Take a deep breath and let your body settle into the quiet, supportive gravity of the night. Release the tension in your shoulders, allowing yourself to drift into the vast, comforting darkness of the cosmos. Tonight, we are journeying toward the constellation of Taurus, bringing our focus to an awe-inspiring object known scientifically as Messier 45, or more commonly, the Pleiades. Even with the naked eye from your own backyard, you can often see this shimmering, tightly knit cluster of stars, historically known as the Seven Sisters. Here is something remarkable to consider as you relax. When you look up at the Pleiades, the cool, silvery light touching your eyes has been traveling across the silent vacuum of space for approximately 444 light-years. In the grand, sweeping scale of astronomy, a distance of 136 parsecs makes this one of the absolute closest star clusters to our own solar system. Feel the gentle weightlessness of that distance, the quiet realization that you are looking back in time, seeing the stars exactly as they were over 4 centuries ago. Consider the age of this beautiful cosmic neighborhood. In astronomical terms, the Pleiades are exceptionally young. They were born from a collapsing cloud of gas and dust just 100 million years ago, while our own steadfast sun has been burning for roughly 4.6 billion years. These stars ignited during the Cretaceous period on Earth, when dinosaurs like the Spinosaurus were walking our planet. The Pleiades were just taking their first glowing breaths in the dark. Sense the fresh, fierce energy of these young stars, humming with the vibrant momentum of their recent birth. Imagine drifting closer now, leaving the solar system behind, as the blackness of space wraps around you like a heavy velvet blanket. From Earth, we might only easily count 6 or 7 bright pinpricks of light in this cluster. But the reality is staggering. Astronomers have statistically confirmed that the Pleiades is an open star cluster, containing over 1,000 individual members. All of these stars are gravitationally bound together, caught in a delicate slow-motion dance as they drift through the Orion arm of our Milky Way galaxy. The total mass of this cluster is estimated to be about 800 solar masses. That means if you gathered every glowing star, every hidden planet, and every microscopic grain of interstellar dust within it, it would equal the weight of 800 of our suns. Let the immense, stabilizing weight of that gravity anchor your thoughts. As we move nearer, notice the intense sensory experience of their light. The brightest of these stars, named Alcyone, Atlas, Electra, Maya, Merope, Taygeta, and Pleione, burn with a brilliant, piercing sapphire radiance. Picture this icy blue light glowing brightly against the absolute pitch-black canvas of space. It might look cold from afar, yet these are B-type stars, incredibly massive, highly luminous, and unimaginably hot. Their surface temperatures range from 10,000 to an astonishing 30,000 Kelvin. For context, the surface of our own warm yellow sun is a comparatively mild 5,778 Kelvin. The intense, radiating heat of these blue giants creates a powerful solar wind, a steady stream of charged particles that sweeps quietly across the silent void. You can almost feel the gentle pressure of that stellar wind, a cosmic breeze blowing through the dark. Let your mind linger on Alcyone, the brightest star in the entire cluster. To an observer on Earth, it has an apparent magnitude of 2.86, making it a prominent jewel in the winter sky. But up close, floating in the quiet space beside it, its power is absolute and mesmerizing. Alcyone is roughly 1,000 times more luminous than our Sun. Imagine resting safely at a great distance from it, feeling the sheer outpouring of its energy, a silent, continuous vibration of light and warmth radiating outward into the freezing, empty expanse. It is a beacon of profound, enduring warmth in the cold of the universe. Now, consider the rhythmic, mechanical movement of these massive celestial bodies. You might instinctively picture stars as perfect, perfectly still spheres of fire. But the brightest stars in the Pleiades are spinning at a dizzying pace. They rotate at extreme velocities, ranging from 150 to 300 kilometers per second at their equators. Focus your mind's eye on the star Pleione. Because it spins so incredibly fast, the centrifugal force pushes its matter outward, meaning Pleione is not a perfect sphere at all. It is oblate, bulging significantly at its equator, much like a spinning top pressing outward against the dark. This rotation is so fast, so extreme, that Pleione literally sheds its own outer layers. The star creates a flattened, circumstellar disk of gas expelled directly into space from its equator. Imagine the smooth, fluid texture of that glowing, ethereal ring of gas, suspended silently in the dark, spinning in perfect harmony with the star it surrounds. While as we glide deeper into the center of this cluster, you might notice a soft, hazy glow surrounding the brilliant blue stars. The Pleiades are currently passing through a vast, wispy interstellar cloud of dust and gas. The intense radiation from the bright stars reflects off this material, creating what astronomers call a reflection nebula. Specifically, around the star Merope, we find a particularly dense, glowing area known as the Merope Nebula, designated formally in astronomical catalogs as NGC 1435. Here is the beautiful, comforting physics behind what you are seeing in your mind's eye. The dust particles drifting through this region of space are rich in carbon, and they scatter short-wavelength blue light far more efficiently than they scatter longer, red wavelengths. This is the exact same optical effect, known as Rayleigh scattering, that makes the daytime sky blue on Earth. You are floating through a cosmic fog of scattered sapphire light. It is completely silent, softly illuminated in all directions, wrapping you in a calm azure twilight that stretches for trillions of miles. Breathe slowly as you imagine the sheer volume of space this cluster occupies. The core radius, the densely packed glowing heart of the Pleiades, is about 8 light-years across. But the tidal radius, which marks the outer gravitational boundary, where stars are just barely held together by the cluster's collective pull, spans roughly 43 light-years. To understand that vastness, realize that you could travel at the speed of light, 186,000 miles every single second, for over 4 decades, and you would only just cross from one side of this starry neighborhood to the other. Let the immense quiet scale of that measurement wash over you. In a space so large, there is no rush. There is only the slow, eternal turning of the cosmos. Yet, for all its brilliant, blazing giants, there are quiet, hidden residents deep within the Pleiades. About 25% of the celestial objects in this cluster are not bright stars at all, but brown dwarfs. These are fascinating celestial bodies, objects too massive to be considered planets, but too small to be true stars. They contain less than 8% of the mass of our Sun. Because they lack the intense weight and pressure required to ignite and sustain regular hydrogen fusion in their cores, they do not shine brightly. Instead, they glow faintly with leftover heat from their formation, irradiating a deep, dull, comforting red against the dark. Think about the texture of these objects. Dense, warm spheres, silently accompanying their brilliant blue sisters through the galaxy. Despite making up a full quarter of the cluster's population, these brown dwarfs are so small that they contribute less than 2% of the total mass of the Pleiades. They are the quiet, unseen companions of the night, holding on to their gentle warmth in the deep freeze of space. There is a deep, soothing rhythm to the life cycle of this cluster. An open cluster like the Pleiades is not meant to last forever in its current, tightly bound shape. The stars are only loosely tethered to one another by gravity, and as they travel together through the Milky Way, they encounter immense gravitational tides from passing spiral arms and giant molecular clouds. Astrophysicists calculate that in approximately 250 million years, these gravitational interactions will cause the Pleiades to slowly unbind and disperse. The stars will gently drift apart, eventually becoming solitary travelers in the vast galactic disk. There is no violence in this process. It is just a slow, peaceful scattering, like dandelion seeds catching a soft cosmic wind, carrying their light to new corners of the universe. Humanity has always felt an innate, deeply personal connection to this specific patch of sky. Because of its distinct, shimmering appearance, the Pleiades are intricately woven into human history and memory. They are mentioned 3 times in the ancient texts of the Bible. In Japan, the cluster is known as Subaru, a word meaning to gather together, a name later adopted by the famous automobile manufacturer, whose logo still bears the 6 visible stars today. When you look up at the night sky and find this small, brilliant cluster, feeling the cool night air on your skin, you are participating in a profound human tradition of quiet observation. You are sharing a view that has comforted humanity for millennia. As we continue to drift effortlessly through this magnificent blue cloud of stars, notice the profound stillness of the vacuum around you. You can almost feel the faint ancient warmth of 1,000 distant suns brushing against you, millions of miles away from any solid surface, safe in the cradle of the cosmos. You are bathed in the scattered light of Messier 45, enveloped in the soft blue fog of the Merope Nebula, floating completely weightless in a pocket of the universe that is 100 million years in the making. As you remain suspended in the soft blue fog of the Reflection Nebula, allow your mind to journey back through the corridors of human memory. The connection we share with these specific stars is ancient, written into the very fabric of our earliest civilizations. Long before humanity understood the mechanics of gravity or the nuclear fusion powering these blue giants, we were looking up, using this bright cluster as a quiet, reliable timekeeper in the boundless depths of the night sky. Take a moment to reflect on the oldest known depiction of the cosmos ever discovered. It is an artifact called the Nebula sky disk, unearthed in present-day Germany, or dating all the way back to the early Bronze Age, roughly 1600 BC. Picture the texture of this ancient object: a heavy circular bronze plate, heavily oxidized into a deep, rich green patina, inlaid with carefully placed symbols of gold. Among the golden moon and the sun, there is a distinct cluster of 7 gold dots. Even 3.5 millennia ago, humans recognized the Pleiades as something profound, hammering its shape into precious metal to carry a piece of the heavens down to the earth. Notice how seamlessly these distant suns wove themselves into the rhythm of human survival. The very name, Pleiades, most likely originates from the ancient Greek word plane, which simply translates to sail. In the ancient Mediterranean world, the first visible appearance of this star cluster in the early morning sky occurred in May. This specific astronomical event signaled to ancient mariners that the dangerous winter storms had passed and the safe sailing season had finally begun. To the sailors of antiquity, the gentle blue light of these stars was a comforting promise of calm waters and safe passage across the sea. Across the globe and across different eras, human eyes traced the exact same slow, sweeping orbit of the Earth by watching when these stars reached their highest point in the sky. Celtic traditions intimately linked the highest midnight elevation of the Pleiades to the festival of Samhain, celebrated around the 1st of November, a celestial timing that eventually evolved into the modern holiday of Halloween. Deep within the Mesoamerican jungles, the ancient Aztec civilization constructed their entire cosmology around a complex 52-year calendar cycle known as the Xiuhpohualli. The culmination of this massive half-century cycle was the New Fire ceremony. Aztec astronomers would stand in the cool night air atop their pyramids, watching in absolute silence until the Pleiades crossed the exact zenith, the highest vertical point directly overhead, at the stroke of midnight. Only then, at that precise astronomical moment, would they light the ceremonial fires, trusting the perfect, unyielding clockwork of the sky to begin a new era. Thousands of miles across the Pacific, the Maori people of New Zealand look to this same cluster, which they call Matariki. They carefully track its heliacal rising, the moment it first becomes visible above the eastern horizon, just before the sun rises. When Matariki appears in late June or early July, it marks the official beginning of the Maori Lunar New Year. The quiet, rhythmic turning of the cosmos is not just a scientific phenomenon. It is the fundamental metronome by which human culture has kept its time. What astronomers eventually discovered, however, fundamentally changed our relationship with these ancient timekeepers. Picture the scene in the winter of 1610. The Italian polymath, Galileo Galilei, stepped into the cold night air, holding a crude, handcrafted tube made of wood and leather, fitted with perfectly polished glass lenses. He was the very first human being to point a telescope at the Pleiades. For thousands of years, the absolute limit of human biology meant we could only perceive 6 or 7 stars in this space. But as Galileo peered through his lenses, the darkness bloomed with hidden light. In March of 1610, Galileo published a groundbreaking treatise titled Sidereus Nuncius, or The Starry Messenger. In this short publication, he included a remarkably detailed, hand-drawn sketch of the Pleiades cluster. He meticulously mapped not 7, but 36 individual stars, offering humanity the very first proof that the universe was infinitely more populated and far more complex than our naked eyes could ever perceive. This spirit of cataloging the heavens continued to evolve. In the late 18th century, the French astronomer Charles Messier was busy mapping the sky, searching for comets. To avoid confusing static, fuzzy-looking celestial objects with moving comets, he created a famous list of things to ignore, known today as the Messier Catalog. On March 4, 1771, he added the Pleiades to his list, designating it formally as Messier 45, or M45. The inclusion of M45 is historically peculiar. Messier's catalog was intended for faint, easily misidentified objects, and the Pleiades are spectacularly bright and unmistakable. Historians of science note that Messier likely added this obvious cluster to his list for a wonderfully human reason: padding his numbers. He was in a fierce rivalry with another astronomer, Nicolas Louis de Lacaille, and wanted his catalog to reach exactly 45 entries before publication to secure his legacy. Thus, the ancient Seven Sisters were firmly locked into modern astronomical nomenclature. At this very moment, as you envision these stars hovering in the dark, they might seem entirely static, pinned to the black velvet of space. But in the mid-19th century, our understanding of their mechanics deepened profoundly. In 1846, the German astronomer Friedrich Wilhelm Bessel undertook a meticulous study of the cluster's proper motion, the slow, gradual drift of stars across our line of sight. Through painstaking mathematical observation, Bessel proved something revolutionary. He discovered that the stars of the Pleiades were not just a random line-of-sight illusion of stars at vastly different depths. Instead, they were all moving in the exact same direction, at the exact same speed. Think of a murmuration of starlings, a massive flock of birds swooping and gliding together in perfect silent unison across a twilight sky. This was the first definitive proof that the stars of M45 were physically and gravitationally bound together, traveling as a single, cohesive family through the interstellar medium. Modern astronomical instruments have measured this elegant motion with staggering precision. The entire cluster is currently drifting through the vacuum of space toward the constellation of Orion at a velocity of roughly 40 kilometers every single second. Even at this immense speed, the distances of the cosmos are so vast that it will take thousands of years for the human eye to notice any change in their position from Earth. Scientists rely heavily on the Pleiades to understand the scale of the universe itself. In astrophysics, this cluster serves as a vital cosmic yardstick, a fundamental calibrator for the cosmic distance ladder. By knowing exactly how far away the Pleiades are, astronomers can calibrate their instruments and calculate the distances to other, far more distant objects in the galaxy. Because of its critical importance, knowing the precise distance to M45 is one of the most important measurements in modern astronomy. This led to one of the most fascinating scientific controversies of the late 20th century. In 1997, the European Space Agency's Hipparcos satellite, designed specifically to measure stellar distances using a geometric method called parallax, returned a highly unexpected result. The satellite calculated that the Pleiades were only 118 parsecs away. This was significantly closer than previous estimates and sent shockwaves through the astrophysics community. If Hipparcos was correct, our entire understanding of how stars evolve and burn would be fundamentally flawed. It required decades of technological advancement to solve the mystery. Finally, in 2014, astronomers utilized a global network of massive radio telescopes working together in a technique called Very Long Baseline Interferometry, or VLBI. By linking radio dishes spread across the Earth, they created a virtual telescope the size of our entire planet. This incredibly precise measurement resolved the debate once and for all, proving the distance to the Pleiades is exactly 136.2 parsecs. The Hipparcos satellite had been subject to an incredibly subtle, systematic error. The models of stellar physics held true, and the comforting certainty of mathematics was restored. Breathe in the quiet stability of those numbers. The laws of physics are consistent, reliable, and deeply serene. As we observe the chemical composition of these stars, spectroscopes reveal that they possess a metallicity very similar to our own sun. In astronomy, metallicity refers to the fraction of a star's mass that consists of elements heavier than hydrogen and helium. The stars of the Pleiades contain roughly 1 to 2% of these heavier elements. This means that within the blazing blue fires of these distant suns, there are faint traces of carbon, oxygen, and iron, the exact same fundamental building blocks that make up the Earth, the oceans, and the very air you are currently breathing. You are deeply and molecularly connected to the ancient light of this cluster, sharing a silent lineage of stardust with the celestial bodies that have guided human history for thousands of years. Rest in that connection, anchored by the slow, beautiful clockwork of the sky, as we trace the invisible lines of gravity binding this stellar family. Chansei, allow your focus to drift toward a seemingly ordinary star, known to astronomers as HD 23,514. What is happening now around this specific star is a story told entirely in the invisible warming spectrum of infrared light. In 2007, the Spitzer Space Telescope, floating silently in an Earth-trailing orbit, turned its delicate supercooled infrared sensors toward this exact coordinate. Scientists discovered something extraordinary hidden in the dark. HD 23514 is surrounded by a massive, sprawling circumstellar dust disk. The volume of material here is staggering. The telescope detected hundreds of thousands of times more dust orbiting this star than we have in our entire solar system. To visualize this, imagine the space between our Earth and the Sun. On a clear summer day, the air feels completely transparent, empty of obstruction. But around HD 23,514, it is like peering through a dense, glittering blizzard of incredibly fine, warm sand. The temperature of this swirling dust cloud hovers around 600 Kelvin. That translates to roughly 620 degrees Fahrenheit, or 326 degrees Celsius. It is a measurement you might intimately recognize. It is the exact, steady, radiating warmth you would feel if you were standing near a traditional, wood-fired stone pizza oven. This cosmic dust is glowing with that exact same deep, baked heat, radiating quietly into the freezing vacuum of space. Astrophysicists understand that this warm halo of powder is the aftermath of a monumental event, the collision of two terrestrial rocky planets. Think of two massive spheres of stone, perhaps the size of our own Earth or Venus. Instead of a sudden, loud explosion, you may imagine this process playing out in profound, slow-motion silence over thousands of years. Like two giant marbles gently but relentlessly grinding together in the dark, their surfaces crumbled and pulverized, softening into a magnificent glowing ring of powdered rock. The violence is long gone, replaced by a smooth, orbiting ribbon of warm dust, patiently waiting to clump together and form new worlds all over again. Deep within the cluster, hidden entirely behind the blinding glare of the famous blue giants, exists a completely different population of stars. These are the red dwarfs, formerly classified as M-type stars. These small, cool objects actually make up the vast majority of the stars in the Pleiades, just as they account for roughly 75% of all the stars in the known universe. Think of the brilliantly hot, blue stars of this cluster as the roaring, towering flames of a fresh bonfire. In contrast, these M-type red dwarfs are the thousands of quiet, long-lasting embers, glowing softly at the very bottom of the hearth, maintaining their steady, low heat long after the bright flames have moved on. Despite their calm appearance and small stature, these red embers harbor intense, invisible energy. The Rosat satellite, a remarkable piece of engineering launched into orbit in 1990, spent years surveying the sky for X-ray emissions. When it pointed its instruments at Messier 45, the darkness suddenly lit up with hundreds of glowing X-ray sources. Because these red dwarfs are so young, in astronomical terms, they are spinning incredibly fast. This rapid rotation turns the entire star into a massive, churning magnetic generator. The process is remarkably similar to a traditional dynamo attached to a bicycle wheel. Just as the physical spinning of the bicycle tire generates a steady electrical current to power a small headlight, the rapid spinning of the stellar core generates powerful, twisting magnetic fields. These fields eventually snap and release energy, projecting silent bursts of X-rays into the void. It is a perfect mechanical conversion of motion into light, happening continuously across hundreds of small stars. Consider an astronomical puzzle that long challenged our understanding of how stars age. The mathematics of the cosmos always leave clues, and the Pleiades offer a fascinating paradox regarding white dwarfs. A white dwarf is the final, incredibly dense, burned-out core of a dead star. Scientists have identified several of these stellar ghosts within the Pleiades, most notably one designated as WD0349+247. The mystery lies in the timing. We know the cluster is roughly 100 million years old, but for a star to be born, burn through its entire supply of hydrogen fuel, die, and collapse into a white dwarf in such a short window of time, it must have been an absolute titan, at least 8 times more massive than our Sun. Massive stars burn through their fuel exponentially faster than smaller ones. Yet, there is a strict, unbreakable rule in astrophysics known as the Chandrasekhar limit. Discovered by the brilliant physicist Subramanian Chandrasekhar, this law dictates that a white dwarf cannot possibly possess a mass greater than 1.4 solar masses. If it does, the immense weight of its own gravity will crush the dead core entirely, forcing it to collapse into a neutron star or even a black hole. So, how does a massive 8 solar mass giant transform into a quiet 1 solar mass white dwarf without destroying itself? What happens is a profound mechanism of shedding weight. Imagine a majestic hot air balloon slowly losing altitude. To prevent a crash, the pilot must begin untying and releasing heavy sandbags, letting them fall away so the balloon can stabilize and remain aloft. The massive progenitor stars of the Pleiades did exactly this. Long before their cores collapsed, they generated fierce, howling stellar winds. Over millions of years, these winds essentially boiled the star away, blowing the outer layers of gas deep into interstellar space. Like a whistling kettle steadily releasing its water as invisible steam, the star shed over 80% of its total mass. By the time the nuclear fires finally extinguished, only a small, manageable core remained, a dense, white-hot sphere about the physical size of the Earth, resting peacefully within the required weight limit. It is a beautifully elegant balancing act, ensuring stability in the aftermath of a star's life. Notice how human ingenuity continually finds new ways to read the history of the universe. To truly confirm the age of the Pleiades, astronomers turned to an incredibly precise chemical indicator known as the lithium test, or the lithium depletion boundary. Lithium-7 is a remarkably fragile element. It is one of the few elements created during the Big Bang itself, but inside the furnace of a star, it is highly vulnerable. Physics dictates that the exact moment a star's core temperature reaches 2.5 million Kelvin, lithium is completely destroyed by nuclear fusion. The relationship is absolute and mathematically pure. Just as you know with utter certainty that a block of solid ice will begin to melt the second the surrounding temperature rises above 32 degrees Fahrenheit, astrophysicists know that lithium cannot survive a core temperature of 2.5 million degrees. This provides an impeccable cosmic thermometer. If an object in the Pleiades still contains traces of lithium, its core has simply never reached that critical temperature threshold. In the late 1990s, an international team of researchers utilized the Keck Observatory to search for this fragile element. Picture the setting of this massive telescope. Housed inside a gleaming silver dome, perched high atop the dormant snow-dusted volcano of Mauna Kea in Hawaii, surrounded by the thin, freezing air of the Pacific night. From this quiet mountain peak on Earth, the telescope analyzed the faint, red light trickling down from a brown dwarf in the Pleiades, known as PPL-15. The spectroscopic data revealed the unmistakable delicate chemical signature of intact lithium. Because brown dwarfs slowly cool and contract over time, their core temperatures rise at a predictable mathematical rate. By calculating exactly how long it would take an object like PPL-15 to approach, but not quite reach, the 2.5 million Kelvin threshold, scientists could refine the age of the entire stellar family. And the math returned a precise answer. The cluster has been shining for exactly 115 million years. Allow the quiet perfection of that measurement to settle over you. From a freezing mountaintop on Earth, peering through the dark at a faint red ember, human minds used a fragile primordial element to tell the exact time on a clock situated trillions of miles away. The universe operates on a system of absolute, unyielding logic. Every temperature, every chemical reaction, every slow rotation and magnetic pulse is part of a grand, interconnected mechanism. As you float alongside the warm, powdery ring of a pulverized planet, or drift past a massive blue star, silently shedding its weight into the ether, you are witnessing the perfect mechanical harmony of nature. Everything is exactly where it is supposed to be, functioning exactly as it must. The physics of the dark are dependable, steady, and incredibly serene. Scientists discovered yet another layer of this mechanical harmony by employing an instrument uniquely designed for absolute unwavering patience. In the late months of 2014, the Kepler Space Telescope, operating under its repurposed K2 mission, was instructed to point its delicate silicon sensors toward the Pleiades. For 71 continuous days, Kepler did not blink. It hovered in the freezing void, staring fixedly at these stars, measuring the exact number of photons trickling into its camera every single minute. What's happening now within that data reveals the beautifully turbulent nature of stellar youth. By tracking minuscule dips in the brightness of these stars, astrophysicists identified massive, swirling magnetic storms on their surfaces, known as star spots. You are likely familiar with the concept of sunspots on our own local star. On our mature, middle-aged sun, these dark, cooler magnetic patches rarely cover more than 1% of its total surface area. But Kepler revealed that the young, rapidly spinning stars of the Pleiades are heavily cloaked in these storms. Some of these star spots are so immense, they cover up to 30% of a star's entire surface. Think of these massive cooling storms as the temporary tumultuous blemishes of youth. Just as human beings go through periods of rapid growth, intense change, and restless energy before settling into the steady rhythms of adulthood, these young stars are simply experiencing their own cosmic adolescence. They are burning brightly, spinning frantically, and constantly reshaping their magnetic fields. There is a deep, comforting familiarity in knowing that even massive celestial bodies must endure a chaotic youth before finding their permanent, quiet equilibrium. Picture this for a moment. What would your everyday life look like if our Earth were orbiting a star deep within the central core of the Pleiades. Astrophysics provides a highly precise answer. The stellar density in the heart of this cluster is approximately 1.5 stars per cubic parsec. To put that measurement into perspective, the local neighborhood surrounding our Sun is remarkably empty, with a density of only 0.14 stars per cubic parsec. If you were standing on a hypothetical rocky planet in the center of Messier 45, your night sky would be transformed. The utter blackness we experience on Earth would be banished. Instead, your sky would be saturated with brilliant, localized light. You would see dozens of stars shining with the intensity of a full moon, casting sharp, overlapping shadows across the ground in multiple directions. You would be wrapped in a continuous, soft twilight, safely held within a tightly packed family of light. It is a reminder that while our own solar system travels through a relatively quiet, solitary stretch of the galaxy, the universe also contains these vibrant, glowing neighborhoods where the dark is kept firmly at bay. Deep within this crowded neighborhood, many stars are not navigating the galaxy alone. At this very moment, direct your attention to Taygeta, one of the prominent blue stars visible from Earth. Through a backyard telescope, it appears as a single piercing point of sapphire light. But the mathematics of spectroscopy tell a different story. Taygeta is actually a spectroscopic binary system. The primary star, known as Taygeta A, is a massive giant, pouring out an astonishing 600 times the luminosity of our Sun. But closely tethered to it by the invisible, unyielding bonds of gravity is a secondary companion star. You cannot see this companion, yet we know with absolute certainty it is there because of the gravitational waltz they perform. Every 1,313 days, this hidden companion completes one full, steady orbit around Taygeta A. There is profound comfort in this silent partnership. Even in the absolute zero of outer space, celestial bodies find balance in one another, offering invisible structural support as they travel through the dark. Notice how gravity continues to shape the long-term architecture of the entire cluster through a slow, majestic process called dynamical friction. Over the past 115 million years, the Pleiades have been unknowingly organizing themselves. This phenomenon is also known as mass segregation. Imagine walking along a quiet, shallow riverbed and observing how the gentle, rhythmic current naturally sorts the stones beneath the water. The heavy, dense, rounded river rocks sink firmly into the deepest central trenches of the channel, while the fine, lightweight sand and silt are effortlessly swept outward, settling along the slow-moving, shallow edges. Mass segregation acts exactly like this current, serving as a cosmic centrifuge. Through millions of tiny gravitational nudges, the heaviest, the most massive blue giants have slowly sunk down into the very center of the cluster, packing tightly into a core roughly 8 light-years wide. Meanwhile, the smaller, lighter brown dwarfs and cool red stars have been gently pushed outward, migrating into the wide, sparse outer boundary known as the cluster's corona. The universe is endlessly patient, taking millions of years to beautifully and meticulously organize its creations. Consider how delicate the balance of this organized family truly is. The binding energy holding the Pleiades together is finite. In astronomy, an object must reach a specific speed, known as escape velocity, to completely break free from the gravitational pull of its neighbors. For the Pleiades, that escape velocity is incredibly low, roughly 3 kilometers per second. If any star in this cluster is nudged by a passing molecular cloud or perturbed by a neighboring giant, and its speed increases beyond that 3 kilometers per second threshold, it will silently slip away from the group. It will cross the tidal boundary and step out into the wider galaxy as a solitary traveler. This mechanism of departure connects deeply to our own existence. Every single atom in your body, the chair you are resting on, and the air filling your lungs resides in a solar system that went through this exact same process. Astrophysicists know that 4.6 billion years ago, our sun did not form in isolation. It was born in a massive, crowded stellar nursery, very much like the Pleiades, surrounded by hundreds of sibling stars. Over millions of years, as the cluster drifted through the Milky Way, those siblings gently exceeded their escape velocities and drifted apart. When you look at the Pleiades, you are essentially looking at a mirror reflecting the ancient, long-forgotten childhood of our own solar system. We are the scattered travelers of a dissolved family, successfully navigating the galaxy on our own. You carry the legacy of that journey within you. The separation was not a tragic loss, but a beautiful, necessary dispersal, spreading light and the potential for life into the quiet corners of the Milky Way. The overarching journey of both our Sun and the Pleiades is governed by the supermassive black hole at the center of our galaxy, located approximately 26,000 light-years away. Caught in the grand sweeping gravitational tide of the Milky Way, the Pleiades cluster is currently traveling in a massive orbit around the galactic center. It takes roughly 225 to 250 million years for the cluster to complete one single lap. This immense measure of time is known as a galactic year. Since their birth, the stars of the Pleiades have not even completed half of a single galactic year. They are infants on their very first ride around the brilliant spinning carousel of the Milky Way. Breathe into the thought of the chemistry happening right now in that distant cloud. The intense ultraviolet radiation pouring out of these young blue stars is actively illuminating the surrounding interstellar gas. Scientists have mapped this region and detected traces of specific isotopes, such as carbon-13. This same isotope, forged in the hearts of ancient stars and scattered by stellar winds, is currently woven into the cellular structure of your own skin. The complex organic molecules required to build biological life are actively being formed in the cold dust lanes of the Pleiades, catalyzed by the warmth of young starlight. The gap between you and the quiet void of space is an illusion. The boundaries between the heavy iron in your blood, the calcium fortifying your bones, and the pulverized, glowing planetary dust orbiting star HD 23514 are remarkably thin. You are an intricate, walking, breathing manifestation of the same physical laws governing these giant spheres of gas. The universe is not some distant, detached void existing far above your head. It is here, folding inward, experiencing itself through your calm, steady awareness. As you rest in the dark, you are exactly where you belong, moving in perfect rhythm with the slow turning clockwork of the galaxy. Sinking further into the quiet mechanics of this stellar family, permit your awareness to focus on the invisible internal rhythms of the stars themselves. You might wonder if the vacuum of space is truly silent. While it is true that sound cannot travel through the empty interstellar void, the stars themselves are vibrating with continuous roaring acoustic energy. Through a specialized branch of astrophysics known as astroseismology, scientists study the internal sound waves bouncing around inside stars. Observe a star in the Pleiades designated as V650 Tauri. This specific celestial body belongs to a classification known as a delta Scuti variable. The physics governing this star cause it to physically expand and contract in a rhythmic, predictable cycle. Deep inside V650 Tauri, massive layers of ionized helium build up, trapping the star's internal radiation like a heavy insulating blanket. As the heat builds, the star expands outward. When it expands, the gas cools, releasing the trapped energy, and the star gently deflates again. This constant rhythmic breathing creates immense acoustic waves that ripple through the stellar plasma. Imagine the star as a colossal, perfectly cast bronze bell. When a bell is struck, sound waves echo endlessly within its metal curves, creating a deep, resonant hum. V650. Tauri is ringing in the exact same way, vibrating with deep structural sound waves that astronomers can actually measure as tiny pulsing fluctuations in its brightness. The universe is filled with this silent, rhythmic drumming. Now, shift your attention outward, from the ringing core of the star to the texture of the glowing blue fog surrounding the entire cluster. For decades, astronomers assumed that this sprawling reflection, nebula, was the leftover birth cloud, the original nursery of gas from which the Pleiades were born. But the exquisite precision of modern spectrometry reveals a different story entirely. The chemistry simply does not match. The Pleiades cluster and the glowing gas cloud it occupies have completely different chemical signatures and trajectories. What you are witnessing is a magnificent cosmic coincidence. The star cluster is currently plowing directly through an entirely separate, unrelated interstellar gas formation known as the Taurus Auriga complex. The cluster is moving through this alien cloud at a relative speed of 11 kilometers per second. Because of this relative motion, the interaction between the bright blue stars and the cold gas is not smooth. At the leading edge of the cluster, the powerful stellar winds generated by the massive giants collide with the stationary gas of the Taurus Auriga complex, creating what physicists call a bow shock. Think of the smooth, curving wave of water that forms at the very front of a ship's hull as it glides steadily across a quiet lake. That exact same fluid dynamic is occurring here on a scale of trillions of miles. The stellar wind acts as the hull, pushing against a frictionless ocean of stardust, creating delicate sweeping ripples of compressed gas in the absolute zero of the void. Observe the physical structure of this compressed gas. Through the infrared sensors of the WISE space telescope, scientists have mapped the exact distribution of the dust. It is not a uniform, featureless haze. Instead, the nebula is highly striated, organized into thousands of long, distinct, thread-like filaments. The elegant logic behind this ribbed texture lies in the invisible architecture of galactic magnetism. The Milky Way possesses its own sprawling magnetic field, and the tiny, microscopic dust grains in this cloud are highly sensitive to it. Because these grains are slightly elongated and carry faint electrical charges, they physically align themselves with the magnetic field lines. Picture the classic science experiment, where iron filings are sprinkled over a piece of white paper resting on a bar magnet. The scattered metal instantly snaps into perfect curving lines. Across 40 light-years of space, the dust of the Pleiades is snapping into perfect parallel lines, drawing the invisible magnetic contours of the galaxy in strokes of blue light. Drop your awareness into the temperature of this sweeping dust. The brilliant B-type stars may be burning at 30,000 Kelvin, but the interstellar gas they are illuminating is profoundly cold. The ambient temperature of the Taurus Auriga cloud hovers at approximately 100 Kelvin, which equates to a freezing negative 280 degrees Fahrenheit. The sensory contrast here is absolute and breathtaking. Massive, blistering spheres of sapphire fire are rushing through a freezing, motionless ocean of frost. The boundary where that extreme heat meets that extreme cold is where the most intricate chemistry of the universe takes place. Within this frigid, glowing fog, say, ultraviolet photons from the stars are actively stripping electrons away from the molecules, drifting in the dark. This high-energy process illuminates a very specific chemical compound dispersed throughout the cloud. Polycyclic aromatic hydrocarbons, commonly referred to as PAHs. These organic molecules are incredibly resilient, surviving the harsh, freezing radiation of deep space. What makes their presence so fascinating is how intensely familiar they are to the human sensory experience. On Earth, PAHs are formed through incomplete combustion. They are the exact same chemical compounds found in the dark soot of a chimney, the charred wood of a dying campfire, or the blackened crust of burnt toast. If you could somehow stand in the vacuum of space, pull off your helmet, and breathe in the Pleiades Nebula, it would not smell like an empty void. Astronauts returning from spacewalks frequently report this exact phenomenon, noticing a distinct, lingering scent on their spacesuits. The reflective fog of M45 carries the deep, smoky, aromatic scent of burnt charcoal and extinguished fires. It is a strangely comforting realization. The building blocks of organic life, drifting hundreds of light years away, smell exactly like a quiet evening, sitting around a warm hearth on Earth. Let your focus drift gently toward Electra, the third brightest star in this vast family. As we observe the light pouring from this specific giant, we find a beautiful anomaly in the spectrum of colors. Electra is rotating incredibly fast, spinning at an equatorial velocity of roughly 170 kilometers per second. And this immense centrifugal force causes the star to eject a disk of superheated plasma from its equator. This specific type of celestial object is known as a B star. The E in its classification stands for emission, meaning it emits specific brilliant lines of light beyond the standard spectrum. As the fierce ultraviolet light from Electra hits its own expelled disk of plasma, the hydrogen atoms in the gas become highly excited. When the electrons in these hydrogen atoms drop back down to a lower energy state, they release photons at a highly specific frequency, known as hydrogen alpha emission. The mathematics of light are flawlessly consistent. Hydrogen alpha emission occurs precisely at a wavelength of 656.28 nanometers. To the human eye, this specific wavelength manifests as a deep, vivid, ruby crimson. So, while the core of Electra burns with a blinding, icy sapphire brilliance, its surrounding disk is softly radiating a warm, dark red. Imagine the visual texture of that color blending, the crisp, piercing blue of the primary star, filtering through a hazy, spinning halo of crimson plasma. The colors intertwine and spiral outward, a silent, swirling portrait of fluid dynamics and atomic energy painted across the black canvas of the night. Every single detail in this cluster, the deep, ringing acoustic waves trapped in the core of V650 Tauri, the smooth, curving bow shocks gliding through the freezing gas, the perfectly aligned filaments of magnetic dust, the faint scent of charred organic molecules, and the ruby-red glow of excited hydrogen, is part of a continuous, majestic process. The mechanics of the universe are not cold or empty. They are rich, textured, and deeply structured. Rest securely in the knowledge that these processes have been running flawlessly for 100 million years. The laws of thermodynamics, gravity, and electromagnetism require no effort, no intervention, and no rushing. They simply exist, operating in perfect quiet harmony. As you observe the intricate sensory details of this stellar neighborhood, you are safely anchored in a universe that knows exactly how to maintain its own profound, enduring balance. As our journey through the Pleiades gently approaches its conclusion, we must observe the ultimate long-term destiny of this brilliant stellar family. How does a cluster of 1,000 stars gradually come to an end? The dissolution of Messier 45 will not happen all at once. It is a meticulous, step-by-step unfolding over vast epochs of time. To understand this future, astrophysicists utilize complex computational models known as n-body simulations. By entering the precise mass, velocity, and trajectory of all the known objects in the cluster, supercomputers calculate the intricate gravitational tugs occurring between every single star. These step-by-step mathematical projections reveal that the Pleiades will completely disperse in approximately 250 million years. This unbinding occurs through a steady mechanical process called tidal stripping. As the cluster completes its massive orbit around the Milky Way, the immense gravitational field of the galaxy's center continuously pulls at the outermost edges of the group. One by one, in a profoundly slow and patient sequence, these stars located at the tidal radius are gently peeled away. They are coaxed out of the cluster's collective gravity and slip quietly into the wider galactic disk. When they separate, these stars will not simply vanish. They will transition into what astronomers classify as a stellar moving group. This means that hundreds of millions of years from now, the individual stars of the Pleiades will be entirely solitary, yet they will all retain the exact same trajectory and velocity. They will travel like a loose, invisible flock of birds, sweeping silently through the Orion Arm. There is a deep comfort in this process. Even when the family slowly disperses, they continue moving forward in the same direction, forever sharing a common origin. While the cluster spreads apart, the stars themselves will undergo their own internal, irreversible transformations. Observe the brilliant B-type stars, the glowing blue giants like Alcyone and Atlas. Because of their immense mass, their internal process of nuclear fusion is ravenous, burning through their hydrogen fuel reserves at an incredible rate. Step by step, over the next 10 to 100 million years, these specific giants will entirely exhaust the hydrogen in their cores. When that primary fuel is depleted, a precise cascading sequence of events begins. Without the outward pressure of hydrogen fusion, the core of the star contracts. As it shrinks, the internal temperature spikes dramatically, igniting a new phase of fusion. The star begins fusing heavier and heavier elements in distinct sequential layers, much like the rings of an onion. Helium fuses into carbon, then carbon into neon, oxygen, and silicon. In the final step of this atomic chain reaction creates iron. However, fusing iron is fundamentally different from the previous steps. It absorbs energy rather than releasing it. The exact moment the core turns to solid iron, the outward thermal pressure drops to zero. In a fraction of a second, the star collapses inward under the crushing weight of its own gravity. It rebounds instantly in a spectacular, blinding explosion known as a Type II supernova. This explosion is fundamentally a process of creation. The unimaginable heat and pressure of that specific supernova blast forge elements far heavier than iron. In a matter of seconds, the detonation synthesizes trace amounts of precious heavy metals like gold, platinum, and uranium. These freshly forged elements are then scattered outward at thousands of kilometers per second, enriching the cold interstellar medium. The destruction of the star is the exact mechanism required to seed the universe with the materials needed for future rocky planets. For the smaller, less massive stars in the cluster, the ones similar in weight and temperature to our own sun, the evolutionary process is much gentler. When they eventually run out of hydrogen fuel, billions of years from now, they will not explode. Instead, their outer layers will expand tremendously, turning them into bloated red giants. Gradually, over tens of thousands of years, they will gracefully puff away their outer atmospheres into space. This step-by-step shedding creates beautiful glowing shells of expanding gas known as planetary nebulae. The exposed cooling cores left behind at the center of these nebulae will become white dwarfs. When these are incredibly dense spheres, roughly the physical size of Earth, composed almost entirely of crystallized carbon and oxygen. Over trillions of years, these white dwarfs will undergo the slowest thermodynamic process in the universe, thermal cooling. Because they no longer generate new heat, they will steadily radiate their leftover warmth away, dropping degree by degree, until they become completely invisible black dwarfs, blending perfectly into the absolute zero of the void. Every single step of this cosmic recycling directly connects to the warmth and weight of your own body, resting right now. The star formation efficiency of the original molecular cloud that birthed the Pleiades was incredibly low. Only about 10% of the gas actually collapsed into stars, and the vast majority of the cloud was blown away by stellar winds to eventually form other systems. Furthermore, the 1 to 2% metallicity we observed in the Pleiades, the trace amounts of heavy elements mixed into their blue fires, came entirely from a previous generation of ancient stars that underwent the exact supernova process we just explored. This means the physical components making up your biology are incredibly ancient. The calcium fortifying your bones, the iron carrying oxygen in your blood, and the carbon forming the very structure of your cellular walls were all forged step by step in the core of a collapsing star billions of years ago. Even the oxygen you are breathing at this very moment, primarily produced by plants on Earth, is an element fundamentally manufactured during the helium-burning phase of a massive star's life cycle. You are not a distant observer of this slow mechanical unfolding. You are the universe itself, beautifully organized, taking a quiet moment to experience its own majesty. It is time to bring this quiet observation to a gentle, comforting halt. Consider the light leaving the Pleiades right now. Traveling across the vacuum at exactly 186,282 miles per second, it will cross 136 parsecs of empty space, taking exactly 444 years to finally reach Earth. There is no rush in the cosmos. Everything operates on timelines so vast and patient that the worries of a single day simply dissolve into the dark. Draw your awareness back from the reflection nebulae and the pulsing blue giants. Trace the path of that starlight all the way back home. See, move past the outer edge of our solar system, past the quiet orbit of the planets, down through the cool protective layers of the Earth's atmosphere, and return to the absolute safety of your own room. Feel the steady, reliable pull of gravity anchoring you to the bed. The same force that binds 1,000 stars together in the deep dark is currently holding you securely in place, keeping you safe and grounded. As your physical body completely relaxes, recognize that human brain waves during deep sleep, classified as delta waves, pulse at a slow, steady frequency of 0.5 to 4 Hz. This deep, oscillating rhythm is remarkably similar to the structural acoustic waves echoing inside the variable stars we observed. Your body is naturally syncing with the steady, quiet heartbeat of the galaxy. The universe knows exactly how to rest, and so do you. Permit your mind to absorb these final truths as the world fades into peaceful silence. I am safe in the vastness of space. My body is made of ancient stardust, returning to its natural state of rest. I release the events of the day, trusting the slow, patient turning of the earth. The laws of physics hold me securely. The universe is quiet, predictable, and deeply serene. There is nothing I need to do right now. There is nowhere else I need to be. I am entirely supported by the gravity of this planet. Every breath I take connects me to the ancient rhythms of the cosmos. My mind is settling into the comforting void. The dark is a blanket of safety. I welcome the profound, healing stillness of the night. The stars will continue their slow dance while I sleep. Everything is in perfect balance. I am at peace. Good night.